Hey class, eyes on the screen. A force is a push or a pull that acts on an object. Please self-mark in green, do your corrections on the spot. It is either a push or a pull, it can't be anything else. Okay, what is friction? Please take your, go ahead and put a star over here. Definitions are important. Okay, it is a contact force that opposes or tends to oppose motion between surfaces in contact. Yep. Okay, put all these down. If you think that your answer should be accepted, show it to me after class, I tell you. Okay? For now, copy this down first. Yes, it is between surfaces. Can? Okay, so similar to our friction, thus, similar to friction, water resistance will always act in the opposite direction of motion also. So if the fish wants to swim out of the classroom, this way, water resistance will be opposite. If the fish decides to swim to the notice board, water resistance will be towards the whiteboard. Besides water resistance, there is something else that is similar also. Air resistance, yes. So if you are running towards the door from my position, what direction is air resistance acting? Towards the screen. It is opposite direction. But is it significant? It is usually very small, right? So it is not very significant at certain speeds. When your speed goes higher, then it becomes more significant, which is why design is very important. Look at the design of a truck versus the design of a F1 racing car. Is there a difference in the design? The shape, right? How streamlined is it? Very streamlined, so that there is less air resistance. Just like our primary school science, you learn about fishes. The shape of the fish, what does it have? What's the shape of the fish? Streamlined. For it to be able to glide, move quickly through the water because there is less resistance. Okay? So now, IQ question. I drop a box down from the second level to the first level. Okay, listen. I drop a box from the second floor to the first floor. Is there air resistance? What is the direction of air resistance? Upwards. What direction is the box traveling? Good. I kick a soccer ball directly upwards. What direction is the ball moving? Upwards. What is the direction of air resistance? Where is it acting on? Which part of the ball is the air resistance acting on? The top. Okay, so when the ball is moving upwards, when the motion is upwards, this is the motion. This arrow does not represent force. The air resistance looks like this. Air resistance. Okay, this is just a diagram. This is not a free body diagram. If I want to draw a free body diagram, then yes, it will be a box. Okay, this represents the soccer ball, yes. Okay, hang on. What if as the ball travels upwards, eventually it will come to a stop, isn't it? Then it will come down, right? When the ball is traveling downwards, is there air resistance? Yes. Where is the air resistance acting on? Okay, what direction is the air resistance acting on? Upwards, okay? Where does it start acting from? From which part of the ball does the air resistance act on? At the bottom of the ball, so the air resistance looks like this. The free body diagram will therefore look like this. Air resistance. And then we have a weight over here. Okay, which one is greater, weight or air resistance? Weight is greater in this case. So there is a resultant force downwards. Okay? Now, when the ball is traveling upwards, back to upwards again, we are saying that there is air resistance from the top right. Air resistance. Right? And then there is weight acting. What is the direction of the weight? Up or down? The ball is traveling upwards. What direction is the weight? Down. Weight will always point down. Doesn't matter what direction you're moving, weight always points down, even if the ball is traveling up. Okay? So weight downwards this way. Alright? Then why is the ball traveling up? How come all the forces acting downwards, the ball still traveling upwards? What? The force that hits the ball upwards. But yeah, you're right, I give the ball a force, an initial force. But once the ball leaves my foot, is there still any upward force acting on it? Is there anything pulling it up? Have or don't have? What is pulling it up? Is there anything pulling the ball up? Don't have. Don't have. I gave it an initial kick already. It is now traveling upwards. Nothing is pulling it up. But there are forces acting downwards. So the resultant force is still down. Although the resultant force is downwards, it is traveling upwards. Why is this so? We will learn it, I think, next year. Okay? If you are interested to know, right, come and talk to me. We find out a bit more. Okay? But for now, my main point is that, yeah, this is possible. Forces acting in one side, it is actually moving in the other direction. Okay? Okay, I give you another example, very easier to visualize, okay? So we have a car. It is moving in this direction. Can you understand? Okay? Then suddenly, red light. Red light. Okay so far? What will the driver do? Does he stop immediately? He brake, right? When he brakes, is there friction? Okay, what direction is friction? So the friction will act to the left or right? Friction act to the left, huh? Okay, so friction will acting to the left. Now this is the motion, huh? Please take note that this is not a free body diagram. It is not a box over here. And this arrow over here does not represent a force. It just represents the direction of motion. Okay, so horizontally, right? How many forces are there acting on it? Horizontally. What are the two? We see friction acting to the left, isn't it? Okay, some of you are saying, yes, there's air resistance, okay. Since it is still moving to the right, there is a bit of air resistance over here. Is there any other forces acting on it? What other forces are there? Okay, weight, fine. So weight over here. So there's a equal normal force. Any other forces? Any others? I'm interested in horizontally. So here we can see that horizontally there is an air resistance to the left, there is friction to the left. But what direction is the car moving? It is moving to the right, but it is slowing down. Get it? So this is a real life example of forces acting in one direction. The resultant force is in one direction, in this case to the left, but the motion is still to the right. Okay? Okay, now, question 3. Which situations is friction a nuisance? B. Wear and tear. Otherwise, braking, walking on the ground, riding a pen, they are all important uses for friction. Okay, so here we have another free body diagram. Direction of frictional forces. What is the effect of frictional force over here? Slows it down. D. Okay, it is moving to the right, but there is friction, so it slows it down. What is the resultant force in this question? What is the resultant force in this question? Are the forces balanced over here? Are they balanced? No, they are not balanced. It is uneven, right? So which one is the resultant force? Sliding? No. How many forces do you see in this diagram? What are the two? Frictional force is one. What else do you see? Motion? What motion? Are you referring to this arrow? Is this what you're referring to? No, this is not a force. This is just telling you it is sliding towards the right. That is not a force. How many forces are there in this diagram? From what we can see, there is only one. Okay? If you want to complete it, yes, there is weight. Then there is a normal reaction force. Now, the weight and the normal reaction force will be the same, isn't it? Right? So they cancel each other out. Horizontally, how many forces are there? Horizontally, how many? One. There's only one. What is that horizontal force called? Friction. Frictional force. So, what is the resultant force? It is the frictional force. The resultant force is the frictional force. Okay? Now, in this diagram, draw and label all the forces acting for this. So the first pair I need to see will be your normal reaction as well as the weight. Normal reaction must start from the bottom, weight must start from the middle. And these two arrows must have the same length. Cannot be one long, one short, must be the same length. Then you must also label it. And you must use your ruler. So make sure you have all these. Next, we require the push. The push starts from this side. Okay? And we will therefore expect friction at the bottom. As long as your frictional force is shorter than your push force, you're fine. Question 6. These are the diagrams. Please check and self-mark. Next. Which of the following statements about force is false? Which one is false? A force can change the shape of an object. Is it possible? Okay. A force can change the mass of an object. Possible or not? Not possible. Okay, B is the answer. It cannot change the mass of an object because the amount of mass a body has is dependent on the amount of atoms, the electrons, the protons, the neutrons, all these they have mass. So no matter where I put you, whether it is in a classroom, on top of Mount Everest, on the moon, at the bottom of the sea, your mass stays the same, but your weight can change. Okay? Uh-huh. Part C here. So part C, it can change the weight of an object. Part D, it can also change the direction of a moving object. Okay, the only thing it cannot change will be the mass of an object. Now, question 8. A force is applied to a rolling ball in the same direction as its motion. So assume the ball is traveling towards the door. I have a force applied in the same direction, what is the possible effect of the ball? Speed up the ball. So the ball is traveling towards the door. I apply a force in the same direction. It must speed up. V. Now 9. SI unit of a force. What is it? Newton. Capital N or not? It is represented by the symbol N. Capital N. Cannot be small n. Next, the 3 effects of a force on the motion of a moving object. Oh, sorry. Yeah, a force is a vector quantity. Yeah, I wrote it on board just now. It has a direction and a magnitude. It can be represented by an arrow. So the longer the arrow is, the greater the magnitude. Yes? No? No question? Okay, next one. What? Okay, hang on. Okay, 11. These are the things that a force can achieve on a moving object. So it can cause it to speed up or to slow down. It can cause it to stop. It can cause the direction to change. Yes? Yes, you can, but just note that these are the possibilities. Okay? So if you chose to put increase as 1 point, increase the speed, decrease the speed as 1 point, I'm sure you're missing out on either the second or my third point. So put it in as well, so that you have the complete picture. So here another one, put a star beside it, just like our define friction. So define pressure. What is the definition of pressure? Not unit time, unit area. Force acting per unit area. Yes. No. Why per unit mass? Okay, see I've got a, remember we learned from this? What does force acting per unit mass mean? Okay, what does this mean? In mathematics, what will this tell us? Force divided by mass. Okay, now this over here, it is equal to something which I haven't taught you yet. Okay, so not force per unit mass. So pressure, force acting per unit area. Okay, so a similar question over here as our notes. An elephant, mass 3,000 kilograms. Hey, mass 3,000 kilograms. What is the weight? Okay, good. 30,000 newtons. Similar question. A lady of mass 45 kilograms. What is her weight? 450 newtons. Okay, she wears high heel shoes. What? Yes, and weight is a force. Weight is a force. Okay, so for the elephant, each foot has a surface area of 0.4 square meters. For this lady, each heel has a surface area of 0.01 square meters. Assume there is equal distribution of mass on each foot. Calculate the pressure exerted by the high heel for the lady. Okay, so pressure equals to force divided by area. And in this case, the force will be 22,500 pascals. This is wrong. Okay, next. If you don't understand, I'll go and watch the video again or ask your friends or come and ask me. Calculate pressure exerted by the elephant's foot. So here we've got 30,000 newtons divided by this is the area for 4 of his feet. I'm sure you know the answer already. Okay, next. A cube of side 0.2 meters weighing 100 newtons rests on the floor. What is the pressure exerted by the cube on the floor? So force divided by area again. So the cube looks like this. This is 0.2 meters, 0.2 meters. So the area on the ground will be 0.2 times 0.2. This is the area. Show of hands who got this one correct. Okay, put on hands. Next. Now, this is a very popular question. A tank is 5 meters long, 2 meters wide, 0.5 meters deep. When it is filled with water, so completely filled, it has a weight of 14,000 newtons. Okay? So do you understand the question? Understand the question? So depending on how you place this container, it will exert different pressures on the ground. Right? Can you visualize? So different ways of placing it will result in different pressures on the ground. What are the 3 possible pressures that can be exerted by the seawater on the base of the tank? Okay, so in this configuration, what is the base area? In this configuration, if you leave it like this, what is the base area? How do you get 10? 5 times 2. In this configuration, the base is 5 times 2, you get 10 square meters. So the weight, 14,000 divided by 10, gives you 1,400 pascals. Okay, so these are the possible surface areas. We've got 5 times 2, we get 10 square meters. So its corresponding pressure will be 1,400 pascals. That's the first configuration. The second possibility is if I take 2 times 0.5. So now this is my base. Okay, so this container, I rotate it. I let the blue color portion be in contact with the floor. Is the surface area bigger or smaller now? Smaller, obviously smaller, right? So now the area is 1 square meter. Then the pressure will therefore be 14,000 divided by 1 to give us 14,000 pascals. So since the area is now smaller, we expect the pressure to be higher, right? Make sense? And finally, the last possible area will be this in green. What is this area over here? 0.5 times 5. So 0.5 times 5, we get 2.5 square meters. 14,000 divided by 2.5, you get 5,600. So these are the possible pressures. So now another kind of IQ question. If I want you to give me the largest possible pressure, are you going to do all 3 calculations and tell me which is the biggest? If I want the largest pressure, what will you do? Find the smallest area first. Is it very obvious which is the smallest area? Okay, if I want the smallest pressure, are you going to calculate all 3? What are you going to find? Biggest area. Okay? Next, Eskimo. Where does the Eskimo live? Very cold places, right? A lot of snow. Snow is soft. Can you imagine walking on snow? Will you sink into the snow? Yes, likely you will sink unless the snow is very packed. Okay? So, in order for him not to sink into the snow, he wears special shoes over here. there are snowshoes. What will the base area of the snowshoe be compared to the regular shoes we are wearing? Do you want the area to be bigger or smaller? Bigger, so that the less pressure, so that he will not sink. Very good. So this is the pressure. 500 newtons, that's his weight, divided by 0.4. In this case, they tell you that the total area is 0.4. So one of it will be 0.2, the other side will be 0.2 square meters. So this is our No, this should be 625. Is that a calculation error? Okay, what's 500 divided by 0.4? 1250. Okay. So this is okay, yeah, 1250. Next, Tom and Jerry playing football, wet and soggy field. Hey, what do you notice about the difference? What's the difference between these two pairs of shoes? One has studs. Yeah. I heard somebody talk about shoelace. You are right, but is that a physics answer? No, it doesn't mean anything for a physics question. So you can write the color different, the shoelace different. You can write all this, but you still get 0. Okay? So this one has studs. So which most of the time Jerry manages to stay on his feet, Tom keeps sleeping. Okay? So which pair belongs to Jerry? Jerry is the one that stays on his feet. X. Using the concept of pressure, explain why shoe X is better than shoe Y. The spikes have smaller area of contact with the mud, so he can sink into the mud and provide better grip. Therefore, there is increased friction between the shoes and the mud. They add forces when they are in the same direction. We subtract forces when they are in the opposite direction. Different, not good enough. Okay? To obtain the resultant force. Let me tell you why different is not accepted. If I have weight over here, let's say 100 newtons, and I have a force pulling it to the right, 40 newtons. Okay? In this case, can you tell me the resultant force? Can I just subtract 100 from 40 or 40 from 100? Can or cannot? Cannot. They are in different directions, but they are not in opposite direction. Okay? Know the difference. These two cannot subtract. We use other ways to find the resultant force in future. Okay, so in this case, what is the resultant force? This is total of 5 newtons to the left, 11 newtons to the right. Resultant must be 6 to the right. Question 20. Force is applied to a rolling ball in the same direction as motion. Sounds very familiar, right? B, speeds up the rolling ball. Very similar question to what was given earlier. Okay, find the resultant force. Part A. 0 newtons. Do you have a unit? Yes. Part B. Part B, how much is it? 0 also, okay. Question 22. What is the resultant force? 15 newtons to the right. State a force that can be applied to make the forces balanced. Did you say frictional force? Okay, maybe it is not phrased very well. State the magnitude of a force that can be applied to the box to make it balanced. Magnitude. Tell me about the magnitude. 15 newtons. Okay. What direction now? To the left. 15 newtons to the left. What? Is it a must to? Do working. For this part? No need lah. This one very obviously 20 minus 5 mental sums you can get 15 straight away.
Then why do you need the answer key when you get mental?
Because not all will be able to be done with mental sums.
I mean like those that can be done with mental sums.
Then okay lah. Okay, question 23. We've got about 5 more minutes. If I can't finish, I will have no choice but to carry on. Resultant force. How much is this?
8 newtons.
Next one?
2
2 newtons. Okay, good. Yes, to the right. Did they say that taking right to be positive? No, they didn't. So, to the right. To the right. Okay? So far I noticed that this worksheet didn't test on negative forces. So you must know if right is positive, then left must be negative. If left is positive, right must be positive. If left is positive, right must be just opposite. If top is positive, down is negative. Okay. If top is negative, then down is positive. If I make it more generic, I don't want to talk about front, back, left, and right anymore. Okay. I try this direction. If this is negative, then directly opposite, that will be positive. Okay. If this is positive, then directly opposite must be negative. Simple. Okay. Last few already. Oh, last one. Now, a hot air balloon is tied to the ground by 2 ropes, stopping it from taking off. So, this hot air balloon plus this hot air balloon has a couple of forces acting on it. First, it definitely has weight. In this case, the weight is given to be 6,650 newtons to the bottom, towards the ground. Weight is always towards the ground. Then, hot air balloon, right? What direction does it always want to go? It always wants to go upwards. So there is a force pushing it up, right? This force is called the upward force in this case, okay? Now, it is given to us that it is 7,500 newtons. Based on this diagram, upward force 7,500 newtons, weight downwards 6,650 newtons. Based on just these two only, what is the result force? Right? How much is it? 850. How do you get 850? 7,500 minus 6,650. So there is supposed to be a resultant force upwards, right? Meaning it is trying to go upwards. But in this case, is it moving upwards? No, it is not. It is stationary. Why? What is stopping it from going upwards? There are 2 ropes that are stopping it from going upwards. Okay? So therefore, there must be forces acting downwards in order to keep it stationary. Meaning the resultant force must be 0. Make sense so far? When it is stationary, the resultant force over here must be 0. So since I have a downward force 6,650, 7,500 newtons upwards, there must be 2 tension acting downwards in the 2 ropes. I will assume that they are equal. Okay? So this is the answer for part A. And label the force T, tension. I already tell you to label as T, right? So you label it as T. Okay? In this case, if you were to go and touch the rope, is it going to be very slack or taut? You know the difference? Slack and taut? Okay, it's going to be very taut because there is tension inside. Tension is a force. So calculate the magnitude of the resultant force acting on the balloon. Now this is the ropes part B. The ropes are now untied. So the balloon starts to float up. Okay, so resultant force will no more tension already. Resultant force will be 850 newtons. Okay? Now, last one.
Reduce mass.
State the changes you will make to enable it to rise faster. How to make it rise faster? Reduce the mass, okay. When you say reduce the mass, you are actually referring to changing the weight. Because in this topic, we are concerned about forces, not the mass. So we are trying to reduce the mass, therefore we reduce the weight, so that the resultant force acting upwards increases. Okay? This is the changes that you can make to the structure of the balloon. Because the upward force is fixed already, fixed. The weight, you try and decrease it. Alright? Any questions? If not, then all the best for your